In this webcast, we're going to work through a frontier orbital analysis for electrocyclic ring closing reactions. What we're going to discover is that if a molecule underwent an electrocyclic ring opening reaction by, say, the conrotatory process, then its reverse reaction under identical conditions, the ring closing reaction, is also going to go by the conrotatory process. And the same holds true for any reaction that goes by the disrotatory process. Let's begin our analysis by looking at this 4-pi electron butadiene case that ring closes to cyclobutene. Once again, the curved arrows don't help us to determine what's the HOMO and what's the LUMO, but in this case, it's not so crucial because we can see that both of them involve pi bonds, and so we're going to have one pi bond as the HOMO and the pi star of the other pi bond as the LUMO. We'll see as the webcast goes on that it's a pi-type interaction that's involved. The way we're going to do the analysis is to arbitrarily then choose one of those pi bonds as the HOMO and one as the LUMO, and what we want to do is to take those domains of HOMO-LUMO domains and recognize that at the boundary we want to match the phases of the adjacent lobes that are positioned there and there. The reason is because that's where the new pi bond is going to form. And so we want to match the phases between the HOMO-LUMO boundary because it's at that position that the new pi bond will exist. So let's go ahead and do that, and I've arbitrarily assigned the left half of this molecule as the LUMO, pi star, which I'm going to borrow the molecular orbitals from ethylene. The LUMO of ethylene is going to have phases in which the adjacent atoms are phased in the opposite way. The HOMO, which is the right half of this molecule, is going to have the phases on adjacent atoms to be the same, and as I said before, the key thing is I want to match the phases between the HOMO and the LUMO boundaries, so that means I'm constrained to pick the phase at this atom to match the phase at the atom of the LUMO. And in doing so, I need to shade the bottom lobe in order to match the shading on the lobe that's over here from the LUMO. And now, since I know that this part in gold represents the HOMO of ethylene, I need to shade this orbital as well. Now, in carrying out the electrocyclic ring closing reaction, what's going to happen is we need to twist the terminal positions in order to match the phases of the lobes to create the new sigma bond. At the very early stages of the reaction, this is going to be a pi-type interaction. How does that evolve? Well, for example, if I wanted to match the shaded region of the terminal atoms on the left-hand side and the right-hand side, you can see that those shaded regions are above the plane, and the other shaded lobe is going to be below the plane. In order to bring those into a side-by-side arrangement, which at some point it's going to be basically parallel lobes like that, I'll need to twist the terminal position on the left in the clockwise direction, and I'll need to twist the lobe on the right also in the clockwise direction. In doing so, I begin to bring together the shaded lobe on the left with the shaded lobe on the right. Very early on, it's making a pi-type interaction, and obviously as the reaction progresses, it evolves into a sigma-type bonding. And so the conclusion that we reach is that both of these terminal positions must rotate in the same direction, and we have the case that the conrotatory pathway is followed for this 4-pi electrocyclic ring closing process. Remember, the 4-electron ring opening reaction also went by the conrotatory process, and so you can see that these reverse reactions go by the same pathway. This analysis extends to larger pi systems, such as the 6-pi electron hexatriene case or the 8-pi electron octatetraene case. In both of these, we arbitrarily break up the pi system into HOMO-LUMO domains. Where you break up the HOMO-LUMO domains, or how you divide that pi system into HOMO-LUMO domains, isn't so important, but what does matter is that at that HOMO-LUMO boundary, you need to match the phases on those atoms because that's where a new pi bond forms. So in the case of the 6-pi electron system, we have here the HOMO of butadiene phase matched at the boundary so that that's where a new pi bond will develop. We have the LUMO of ethylene on the far left, and in order to match the phases, say the unshaded regions, what we're going to need to do is to rotate these termini in opposite direction. When we do that, rotating in the clockwise direction for the atom on the left, and rotating in the counterclockwise direction for the atom on the right, that brings together these unshaded lobes, first initially in a pi-type fashion, eventually developing into this sigma bond. I'll leave the 8-pi system for you to do on your own, and as you can read about down here, you can dissect this into homo-LUMO domains in any way that you would want. For example, you could choose 2 butadiene molecules if you wanted to, or you could choose, as was done here, the LUMO of ethylene and the HOMO of hexatriene. You'll be led to the conclusion that this is a conrotatory process. In the next webcast, we'll be moving on to look at the sigmatropic rearrangement reactions.